All right, so we talk about this. Now it is a good time to talk about its successor, which is Advanced Encryption Standard, or AES in short, or its original name, Rijndael. So Rijndael was designed by John Damon and Vincent Raymond, both Belgian cryptographers. It was standardized in 2001 by NIST. It was the winner of the AES competition, which was designed by NIST again. And since Rijndael won the competition, it's named as AES. But of course, there are a little bit differences between Rijndael and AES, because AES supports three key lengths: 128-bit, 192, and 256. Actually, in Rijndael, you can choose middle values between them. Also, block size is 128-bit in AES, but in Rijndael, you are allowed to, change it also. But NIST thought that, having too many block sizes would be difficult to standardize, so they tried to fix it to 128. So they won this competition. So Rijndael actually, words from their last names, as you can see. But there were other finalists: Serpent, Twofish, RC6, and Mars. So these are also good ciphers, and they are included in many libraries like OpenSSL and so on. You can use them, but if you have AES, there's no point of using something else, right? So as I already mentioned, the block size is fixed. You have 3 key lengths, but depending on your key length, the number of rounds changes. And it is a SPN block cipher, substitution permutation network. So once your key length increases, number of rounds increases. People think that this is, against the expected, because people thought that if you increase the key length, so it will be more secure, so the number of rounds should be less. So this is counterintuitive, but the idea is as follows. So you have a secret information, and you are trying to feed the secret information to all of the rounds. So if you increase the key length, then it will be harder for you to diffuse it into all of the rounds. So this is why you are increasing the number of rounds. Okay, this is the main idea. Also, once you increase the key length, the security upper bound becomes, for instance, for this key length, becomes 2 to the 256. So the attacker has more freedom compared to 2 to the 128. So increasing the number of rounds here is a good idea. Of course, as you can see, if you move from personal security to military level security, your number of rounds increases from 10 to 14. So there's a 40% increase. So this means that 40% slowdown. So you're only losing speed in terms of 40%. But even in the best case scenarios, if you use this key length, we have very good optimizations for both CPUs, GPUs, or FPGAs, and so on. So AES is really fast in almost any platform. But of course, if you have a very small device, then you might move on to a lightweight algorithm like Present. Okay. So at the end, I will try to show you some CPU and GPU performance results anyway. But let's look at the algorithm design first. So known attacks are ineffective. This is why we are still using AES. But if somebody comes up with a good attack that breaks 10 rounds, then NIST will have to design another competition to replace this AES, okay? Until that time, we will be happy to use AES. And NIST also says that use AES whenever it is possible. But if you don't like it due to, if you're using in a very small device and the throughput is not enough, or if it doesn't fit your device, then you might use a lightweight algorithm. But of course, NIST currently doesn't have a lightweight standard, but the competition is about to end in a few years. So we will have a lightweight alternative to AES. And Snowden documents also show that NSA does not have a way of breaking AES, so we are assuming that it is secure. So before moving on to AES structure, let's recall how the SPN ciphers work. Recall that in a single round, we had 3 layers: add round key, substitution, and permutation. and key schedule provides you round keys from the master key. So AES has a 128-bit block, but in the representations, we show them by 16 bytes, and these 16 bytes are shown as a 4x4 matrix. It is easier to understand the operations once you use this representation. So actually, one round of AES works like this. So you have the input, 128-bit, but again, I show it as a 4x4 matrix. You XOR it with your round key, which is also 128-bit. So you are simply performing a round key operation. You are XORing the input with your round key. Then you perform sub-byte layer. Here you take 1 byte, apply the S-box, which is 8x8 S-box. So it takes an input as a byte and provides the output as a byte. So you provide confusion here, which is effective on bytes. Then you perform a shift row operation. This means that first row stays as the same. This is why this X stays here. But the second row shifted 1 byte to the left. So this X goes 1 byte to the left. So this byte becomes the rightmost byte in the following round. So second row shifted 2 bytes, and the third row shifted 3 bytes. Of course, if you start numbering the rows from 0, 1, 2, 3, so you rotate them to the left that many bytes. So here we obtain confusion on the byte level. Here we obtained diffusion in the row level, but we didn't mix columns here. So this is why you have a matrix multiplication here. You take this column, multiply it with the matrix, then the result is written to this column. Then you apply the same thing to this column. You take it, multiply with the matrix and write it here. So these two parts provide you diffusion here at the row level, here at the column level. This part provides you confusion. And before that, you apply the head-round key. Okay. So I will show them in detail in a minute, but you can also think about 2 different ways of AES representation. So a byte can be treated in 2 ways when dealing with AES. A byte can be viewed as a string of 8 bits, since this is how you represent a byte. But here we are actually performing some field operations. So you can also view a byte as an element in the Galois field 2 to the 8. But in order to talk about this, we need to talk about what a group is, ring is, field is, and so on. So to avoid that, people generally focus it as bits and just take the implementation and work on that instead of dealing with the Galois fields. But in the arithmetic in the Galois field works as follows. AES uses the Galois field defined by the irreducible polynomial. So as you can see, this is a degree 8 polynomial. So when you perform operations like multiplication here, the result might exceed the degree 8. You actually divide it with this polynomial, so you're working on the remainder. So a byte can be represented by a degree 7 polynomial, where the bits of the byte correspond to coefficients of this polynomial. Now we can perform addition and multiplication on these polynomials modulo RP. So here the division operation is by this polynomial. This more mathematical representation is better to understand the security of the cipher, and it requires more technical detail. So you can see as you like, but know that there is a mathematics behind it. So a round function of AES is as follows. I already show you the big picture, but it starts with key addition, which is just XOR of the round key. Then sub-bytes uses 8x8 S-box, applied to all of the bytes. Then shift rows, which is just a rotation to the left. And then mixed columns, which is multiplication by matrix M. Since this is an SPN, in the decryption part, you have to perform the inverse of all of these operations. So for the mixed columns, you multiply with this time with the inverse of this matrix. Then in the shift rows, you rotate right instead of left. And for the S-box, you just use the inverse of the S-box. XOR operation is inverse of an XOR operation is the same, so you don't rotate, you don't change anything. And let's look at the key schedule of AES. This picture from the book by Lars Knudsen and Matthew Robshaw. The title of the book is The Block Cipher Companion. So your master key, 128-bit key, is written here and represented as 32-bit values. So the rightmost 32-bit value is taken here, rotated 1 byte to the left. Then sparks is applied to all of the bytes. Then a round constant is added to the left part, left byte. Then this one is XORed to this part. It is XORed to this part, and this part. So this is your second round key. You perform this operation again and obtain the third round key, and so on and so forth. These round constants are just values obtained via the Galois field. Okay. So as you can see, everything is really simple. But the important thing is that if this round constant were added to all of the bytes, we could actually find 2 to the 32 weak keys for AES. In a very recent study, we found that kind of a weakness to other key schedules proposed by other people. But for this case, this breaks the symmetry. So this is why our attacks only works for like 5 or 6 rounds. But, it is for the cryptanalysis part. Okay, so let's look at all of the steps one by one. In the first step, we have the add round key. So this is your input. So this is your round key. What you do is as follows. You actually XOR this 128 bits with this 128 bit. But at the byte level, what happens is as follows. You take this byte, XOR it with this byte, and write it to this place. This is how the add round key works. Okay. Of course, in implementation, most of the time, it is easier to work on 32-bit values, since in C, when you create an unsigned integer, it is 32 bits. So you can represent rows with just 4 values. Then you can just XOR 4 rows here to obtain this part. It depends on your implementation technique, actually. In the sub-bytes, again, the sparks is applied to all of the bytes. For instance, for this byte, you take it, fed it to the sparks, the output is written to here. Okay. And the 8x8 sparks of AES is given with this table. So, for instance, if your input is 3B in the hexadecimal notation, you just look at since 3 represents the row, B represents the column. So you take the third row, and the beat column, and the output is E2. So if you fed S with the input 3B, the result is E2. So this sparks is really important because it is chosen as the inversion of the input byte X when viewed as an element of Galois field 2 to the 8. It provides optimal resistance against linear and differential cryptanalysis. So far, no better sparks is found against differential cryptanalysis. So we haven't talked about cryptanalysis yet, but this is important. So if you can come up with an 8x8 sparks, which provides better resistance against differential or linear cryptanalysis, then it will be a huge discovery. Shift rows, I mentioned that in the 0th row, nothing changes. In the first row, everything rotated 1 byte to the left. So this one goes to the right here. So in the second row, you rotate everything 2 bytes to the left. This one comes here, this one comes here, and this 2 goes here. Similarly, in the last one, you just actually rotate everything to the left 3 bytes. So you take this 3 bytes, put it to the end. As the final part, you perform matrix multiplication. There is a matrix. I will show it in a minute. But you multiply every column with this matrix and write the resulting column here. And this matrix is provided like this in hexadecimal notation. But it is deliberately chosen. So M is derived from the parity check matrix of a maximal distance separable MDS code. So MDS goes beyond the scope of this lecture, but M's feature about branch numbers is important for us. So by the branch number, we mean as follows. So you take one column, multiply with this matrix and write the result as the output. But a matrix is called to have branch number beta if the above equality holds only when either all xi and yi are 0, or there are at least beta non-zero values among xi and yi. So in the case of AES, matrix M has branch number 5, and it allows small changes to affect many bytes. This property provides better security against differential and linear cryptanalysis. So let me explain how this branch number 5 works. So assume that you have a column. You multiply with this matrix and obtain the output. So if you change 1 byte here and keep the others the same, since the branch number is 5, among these 8 values, at least 5 of them should be affected. Since I'm keeping this 3 the same and changing this one, 4 other bytes have to be changed. So this means that all of the yi's has to change. So if you modify a single byte, it affects 4 bytes in the output. So if you affect 2 bytes, if you subtract 2 from 5, it is 3. This means that at least 3 of the outputs should change. So this makes, small changes to be a huge difference. This is why, we say it is from maximal distance separable codes. So from small changes, you have huge distances. That is the main idea. So let's look at the performance of AES. Efficient AES implementations are successfully provided on many software and hardware platforms. Still, lightweight block ciphers are necessary for very constrained devices where AES, cannot fit there due to area, or even if it fits, maybe the throughput is really low or the latency is low and so on. Good thing is that in our CPUs since 2010, I guess, or 2009, we have special instruction sets. So the reason for that was because USA made it a must for state officials to keep their hard drives always encrypted. So when a laptop is stolen or lost, documents cannot leak because the hardware is encrypted. That is the idea. Because people started to, lose their laptops in the airports, so important state documents started to leak. So this is why they made it a must. And another option is to actually what they do is to, give a clean laptop to the person who is traveling. Once they come back, they wipe the drive and, return everything back to original state. So when somebody else is going, they give it again. But if you want to travel with your own laptop, you have to keep everything encrypted all the time. But a full disk encryption results in 20 to 40 performance loss depending on your CPU speed and core number. But encrypting and decrypting huge amounts of data in your hard drive takes a lot of time. Even if you have a fast implementation or optimization, encrypting gigabytes of data takes some time. It is not on the fly. So for this reason, Intel and AMD provided hardware-level AES instructions on their CPUs. So these instructions are on the hardware level, so they work really, really fast. So you cannot compete with them by writing any assembly or C code, okay? These are at the hardware level and they are really fast. Again, there's for instance, simple instruction for a single round AES encryption. But since the last round of AES is different, since there isn't any matrix multiplication, there is a different instruction for the last round. So this is one of the problems when you break the symmetry in the design. So let me show you some CPU and GPU results, and then I will show you the better picture. So when this Intel instruction set were first available, people at Intel actually used this, I think, 6-core CPU, or it was 4, I'm not sure. In 2010, they use a CPU to obtain more than 100 gigabits per second encryption on a single CPU, but of course using all of the cores. So people then, started to optimize AES on GPUs. For instance, this paper is from 2013. They obtained 80 gigabit per second, but they compared their result with CPU implementation, and they said that we are 10 times faster than CPUs, but they forgot to check these Intel instruction sets. Again, 3 years ago, CPUs were faster than GPUs because these CPUs were using hardware instructions. So in a recent study, I wanted to check what happened since then. As you can see, this is the very old generation CPU. I used the 6th generation CPU with 4 cores. I obtained 90 gigabits per second. And also with the, I think 8 core i7. So this is 4 core, this is 8, this is, sorry, 4, 6, and 8. So I obtained 134 gigabits per second. So here I'm trying to show you that CPUs are better than some of the earlier GPU results anyway. So these papers didn't compare their results with the instruction sets, but they, just focused on their own results. And another problem is that, for instance, here in the recent papers, they obtain better gigabits per second, but this is not a correct way of comparing, because saying that it was 80 gigabits in the past and you obtained 200 gigabits now makes no sense, because you are using a GPU from 2013 here, and here you are using a new GPU. So it is not surprising to have better results. So in order to compare these results, you have to have the open source codes so that people can compare their results on the same GPU. Okay, but what I tried to show that I made better optimization. So I obtained more than 300 gigabits per second on the GTX 970. And as you can see, people obtained around 100 gigabits per second on the GPU. So I used the shared memory architecture in a very nice way to get a very good optimization. Then I obtained, 800 gigabits per second for RTX 270. So you actually exceed 1 terabits per second in RTX 3000 series. But now we have 4000 series. I haven't checked yet, but probably you can have more than 100. Sorry, maybe you can exceed 2 terabits per second at the best GPU. But again, this comparison just by looking at gigabits per second is not correct, because here I'm getting very good results compared to CPUs. But this CPU maybe draws 100 watts, but this GPU uses 260 watts. And the better comparison should be energy efficiency. So you should compare gigabit per second per watt. Okay, so here I show the maximum peak watt values for all of these devices. As you can see, a CPU here gets a very nice results. It means that for a single watt, they can obtain 2 gigabits per second encryption. So my best result here, it is 2 times faster than that. I'm just trying to show you that, okay, GPUs are really good, but once you compare it with the hardware level instructions, if you are not moving to my new implementations, then there's no point of using GPUs. You can stick with the CPUs. But at the server side, if you are going to use AES encryption a lot, you cannot use all of your cores at the server just for encryption, because you are going to perform other operations. So what I'm suggesting is to just put a GPU there, get the best result, and reserve all of your CPU cores for other operations. So this will be, very time and energy save for you. As you can see, this is the best results in terms of gigabits per second per watt. And for a server, you will just use one of your PCI Express slots for a GPU and get all of the encryption and decryption free. So, but it is nice to see, the speed, because having 1 terabit per second encryption means that if you are going to encrypt and decrypt your hard drive, your hard disk read and write speeds are not as fast as this one. So this means that you get the encryption free in your personal use cases. Okay. So these are the comparison, currently the very modern results for CPU and GPU performance for AES.